Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Smart Grids, Unit Commitment Optimization. Lecture prepared by Engineer Jesus Velasquez Bermudez, Ph.D. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. Smart Grids, Unit Commitment Optimization. The following information was extracted from Smart Grid Optimization. Presentation realized by Professor Eugene Feinberg, from Stony Brook University at New York. Unit Commitment Problem. The unity commitment, UC, continues to be a fundamental challenge of optimization in electrical systems, focusing on finding the most cost-effective schedule to start and shut down generating units that meet the electricity demand. UC and smart grids. Smart grids have transformed UC from a static, supply-side problem to a dynamic, multi-objective framework. Decentralized resources. Modern UC integrates distributed energy resources, DERs, such as residential solar systems and vehicle-to-grid, V2G, systems, which can serve as flexible loads or incremental providers. Demand response. Unlike traditional systems, where demand is a fixed input, smart grids enable appliance engagement, where thermostatically controlled household loads, e.g., water heaters, are programmed alongside generators. Integration of renewables. UC models now frequently use stochastic or robust optimization to manage the intermittency of wind and solar energy. UC in high tension, high voltage, and transmission. UC evolves into security-constrained unit commitment, SCUC, to ensure grid stability. SCUC incorporates transmission line limits and voltage constraints to prevent overloading high-voltage lines. Frequency stability. With the loss of traditional inertia from rotating thermal turbines, modern UC models increasingly include frequency stability constraints to manage grids with high renewable penetration. Interconnected systems. Advanced frameworks now use decentralized robust UC for bulk AC/DC interconnected systems, coordinating regional power flows to maintain reliability across large-scale high-tension networks. Energy storage is a new component of the models. The unity commitment problem involves given, hourly time horizon, load forecast, and units available for service. Determine units that should be placed online each hour, or day or week or month. The aim is to minimize costs, fuel, own, startup or shutdown, and risk. Constraint spinning reserve, emissions, network ramp rates, and technical electricals. The trickiest part of the problem is related to the start and end of build units, which turns the problem into a binary programming problem. Some related features are nuclear, shut down only for refueling. Renewables, hydro, solar, wind, zero resource cost. Large coal, 250 plus MW, very long start time, days. Gas, less than 200 megawatts, 8 to 24-hour start time. Combustion turbines, as low as 5 minutes. Mathematical formulation. Objective function. Minimize sum of generation costs, reserve service cost, and regulation service costs. Mathematical formulation. Constraints. Load balance. Ancillary service requirements. Total and location-based reserve requirements that include 10-minute and 30-minute spinning and total reserve requirements, and regulation requirements. Transmission constraints, and single generator capacity constraints. Probabilistic unit commitment model with wind power. Assuming a certain level of power outage, a new reserve restriction will be obtained. Rolling horizon scheme of the model is: at each time t, updated wind power forecasts is obtained. Update the reserve constraints, and solve the unit commitment problem with respect to the next t periods. The most well-known solution methods for UC are heuristic methods, mixed integer programming, Bender's decomposition, dynamic programming, Lagrangian relaxation, and utilization of parallel computing. A unit commitment daily schedule is the operational plan that determines which electric generators should be on and off at each hour of the next day to meet projected demand at the lowest possible cost. A weekly unit commitment program is an optimization process that determines the schedule for turning electric generators on and off over a 168-hour, 7 days, period. Its main goal is to minimize total operating costs, such as fuel, startup, and shutdown, while meeting expected demand and safety reserves. Generation optimization with the presence of distributed generation, DG. DG is a feature of the smart grids. DG includes combinations of fuel cells, renewables, microturbines, energy storages, etc., located in the scope of the smart grid. DG is more uncertain, making authorization decisions even more difficult. For example, it is difficult to predict near-term wind availability and speed. Some reasons for DG are: DG units are closer to customers. Therefore, transmission and distribution, TAND, costs are reduced. It is easier to find sites for small generators. Natural gas as fuel in DG stations is easily accessible and prices are more stable. DG plants require shorter installation times, and the investment risk is not too high. DG devices can be strategically placed in power systems for grid reinforcement. Benefits of optimal placement of DG: reducing power losses and on-peak operating costs, improving voltage profiles and load factors, differing or eliminating for system upgrades, improving system integrity, reliability, and efficiency. Transmission networks are usually huge in size, running through several states or even across the international boundaries. They are interconnected, which means that the failure of one region may cause the collapse of the whole network. For this reason, security and reliability issues are of vital importance. The proximity of equipment generates more reliable networks. A mixed integer linear programming based approach for unit commitment in smart grid environment. Having effect on nearly every aspect of industrial productivity and daily life, the power industry, in terms of economic importance and environmental effect, is one of the most important sectors in the world. Unit commitment, UC, involves the determination of on/off status of generation units and the value of generators' power production to meet the forecasted demand for a specified time horizon. The optimal schedule should minimize the production costs of the system during the programming period, while meeting the load demand, rotating reserve requirements as well as the physical and operational constraints of each individual unit. Being a non-convex mixed combinatorial optimization problem, several mathematical methods have been proposed to solve the UC problem. The mathematical approaches include priority list, PL, dynamic programming, DP, mixed integer programming, MIP, linear programming, LP, and branch and bound, BB. Due to some difficulties in solving the problem using exact methods, heuristic approaches have been proposed. Due to some limitations in application and results of the mathematical methods, heuristic approaches have been proposed. In the context of smart grids, unit commitment, UC, is the optimization process that consists of deciding which smart grid generation units to start up or shut down, over a period that typically lasts between 24 hours and a week, to meet electricity demand at the lowest cost. While traditional UC focuses on centralized plants, in the smart grid, UC integrates decentralized resources, making the problem multi-objective and highly stochastic. Key drivers in smart grid unit commitment: renewable energy integration. The intermittent nature of wind and solar requires UC models to account for high volatility on the supply side, often using stochastic programming or hidden Markov models. Demand response, DR. Smart meters enable two-way communication, allowing consumers to shift their load during peak hours. At UC, this means that demand is no longer just an input, but a decision variable. Electric vehicles, EVs, through vehicle-to-grid, V2G, technology, EVs act as mobile energy storage systems, helping to fill charging valleys and reduce peaks. Carbon emission constraints. Modern UC models prioritize reducing environmental impact, often incorporating carbon emissions trading, CET, to balance economic and ecological goals. Smart grids involve an increasing level of intelligence and incorporation of new information and communication technologies into all aspects of the electricity grid. Demand response resources and the network vehicle are two interesting programs that can be used in the smart grid environment. Demand response resources can be used as a virtual power plant on the demand side to improve the safety and reliability of the power company and have the potential to deliver substantial benefits in the form of greater economic efficiency and wholesale electricity markets. An economic model of incentive-sensitive burdens is used based on the elasticity of demand and the benefit function of customers. On the other hand, a grid-tied vehicle can be used as a small portable power plant to improve the reliability and safety of the electrical system. An integer mixed planning model is used to solve the UC problem with demand response resources and network vehicles, and the objective function has been modified to incorporate these aspects. The model test is performed with the conventional 10-unit test system to illustrate the impacts of the smart grid environment on the UC problem. The benefits of implementing demand response resources and grid-connected vehicles in electricity markets are demonstrated. In TBR, the electricity price changes for different periods according to the electricity supply cost. The electricity price are time of use, TOU, real-time pricing, RTP, and critical peak pricing, CPP. In these programs, there isn't any incentive or penalty for customer response. IBPs are grouped into three programs. Voluntary are voluntary programs, and if customers do not curtail consumption, they are not penalized. Direct Load Control, DLC, and Emergency Demand Response Program, DRP. Mandatory, enrolled customers are subject to penalties if they do not reduce measures when instructed. Capacity Market Program, CAP, and Interruptible/Curtailable, IC, service, and Market Clearing, large consumers negotiate load variations at a convenient price. Demand Bidding, DB, and Ancillary Services, as programs. Plug-in hybrid electric vehicles, PHEVs, can draw and store energy from an electrical grid to supply power that allows a PHEV to shift energy from oil to multi-source electrical power. This has an important and generally beneficial influence on oil consumption, pollution, as well as on the performance and composition of the power grid. Due to these characteristics and their short-term availability, PHEVs are considered one of the most promising means of improving the sustainability of energy sectors. PHEVs have economic benefits and a short payback period for owners, help improve the fuel efficiency of light vehicles and significantly reduce oil consumption. In addition, they have achieved high penetration. Nowadays, it has been necessary to consider a widespread adoption of electric vehicles in all activities within electricity systems. However, some activities are likely to undergo more severe modifications, both technically and operationally, than others. Vehicles will be connected to lower levels of the network, and therefore entities active at these levels will be affected. Among the problems, the unit commitment, UC, is one of the activities that are influenced by PHEVs. The image presents the nomenclature of the mixed nonlinear programming model for UC in a smart grid, MIMP-UC. UC consists of determining the activities of all generating units, from an initial hour to meet the load demands associated with the startup and shutdown program over a time horizon. The goal of UC is to find the optimal schedule to minimize total operating costs, while meeting charging demand, mobile reserve requirements, emission permit limits, and other operational constraints. The objective function comprises startup and shutdown costs, fuel costs, as well as the emission level of the generating units. The responsive load economic model is necessary to assess the impact of customer participation in DR programs according to the characteristics of the load profile. In 1989, Schwepp and his collaborators formalized the concept of spot electricity pricing. They envisioned a system in which customers would adjust their demand, upwards or downwards, depending on the price on demand. In 2000, Kirschen showed how this model could be considered when scheduling generation and setting electricity prices in a pool-based electricity market. In 2014, in this article the authors develop models that include penalties and rewards, based on the level of customer demand, depending on their response. The concepts considered are: price elasticity of demand. Elasticity is defined as the demand sensitivity with respect to the price. Modeling of single-period elastic loads. The customer changes his demand from DT, initial value, to DDRT, based on the value which is considered for the incentive and the penalty mentioned in the contract. Modeling of multi-period elastic loads. According to the linearity assumption of cross-elasticity, the relationship between prices and demand is linear, and load economic model. By combining the definitions of elasticity, the responsive load economic model is obtained. Gridable vehicles model. Only the GV recorded are considered to determine the optimal solution in the UC problem. This number it is fixed and is assumed to have been charged with renewable sources rather than smart grids. All vehicles are downloaded to the grid during the scheduling period. MIP-based unit commitment with demand response and gridable vehicles. The model has focused on voluntary DR programs. It is assumed that A and $0 per megawatt hour as the value of the incentive and the penalty, respectively. In these programs, the interconnected system operator, ISO, prizes value customers for the reduction in load, but do not penalize their increase. The objective function is quadratic with respect to the incentive, which gives rise to a mixed nonlinear optimization problem, MNLP, which in 2014 was very complicated to solve using standard nonlinear programming methods, but which today is a manageable problem. The formulation of the MNLP-based model of UC with DR and GV has the following components. Fuel cost. The quadratic fuel cost function is typically used in programming problems. The cost function can be accurately approximated by a set of blocks in parts, which is indistinguishable from the nonlinear model if enough segments are used. Startup cost. Since the time has been discretized into hourly periods, the starting cost is a discrete function, which can be asymptotically approximated by a stairwise function, which is more accurate as the number of intervals increases. Shutdown cost. Shutdown cost is constant for each unit and is modeled by using a shutdown indicator. Total incentive for participation in DR programs. It is a quadratic function of incentive, which can be represented as a piecewise linear model. The figure shows the piecewise linear total incentive curve for an hour. The objective function is subject to the following constraints. Unit output limit. Ramping up-down constraints. Once a unit is compromised, it must remain on for a minimum number of hours, and if a unit is off, it must remain off for a minimum number of hours. A unit may not be started up and shut down in the same hour. Spinning reserve, SR, must be sufficient to maintain the desired reliability of the electrical system. The SR is usually a predefined amount that is equal to the largest unit, or a given percentage of the expected load. Load state, express that each vehicle must have a desired charge level in the output state. Number of discharging vehicles constraint. Not all vehicles can be discharged at the same time due to power transfer and current limit. For reliable operation and control, only a limited number of vehicles can be unloaded at a time. Efficiency. Charging and inverter efficiency should be considered. Simulation cases. A conventional 10-unit test system has been used for simulation studies. The load curve of the 10-unit test system is divided into 3 different intervals. Valley period, 0 a.m. to 5 a.m. Off-peak period, 5 a.m. to 9 a.m., and 14 p.m. to 19 p.m., and peak period, 9 a.m. to 14:00 p.m., and 19 p.m. to 24 p.m. The potential of DRP implementation is 40%, that means that only customer representing 40% of the total load signed contracts for participating in the programs. Therefore, ISO will be able to decrease the peak load of the system about 600 megawatts and to increase the reserve margin and reduce the cost of UC problem as well as the possibility of load shedding. The voluntary IBPs has been introduced in table statement of scenarios. The price elasticity of demand is provided in table price elasticity of demand. 4 different case studies have been considered to show the effect of smart grid environment, including DRPs and GVs, on the UC problem. UC focuses on the problem of conventional unit commitment without considering DRPs and GVs. UC plus DRP focuses on the effect of DRPs on the UC problem. UC plus GV focuses on the impact of GVs on UC problem. UC plus DRP plus GV focuses on the effect of both of DRPs and GVs on UC problem. Parameter values regarding GVR. Maximum battery capacity equal 25 kWh, minimum battery capacity equal 10 kWh, average battery capacity, PGV equal 15 kWh, maximum number of vehicles for power provision at each hour, 10% of total GVs, total number of GVs in the system equal 50, charging discharging frequency, 1 per day, departure state of charge equal 50%, and efficiency equal 85%. Case 1. Conventional unit commitment problem. In this case, the system includes 10 units with a scheduling time horizon of 24 hours. The cost curves for generating units given as a quadratic function are approximated by 20 linear segments between the minimum and maximum generating units capacity. Table 3 shows the MIP-based solutions, outputs, of the units over a 24-hour period for a 10-unit base system, for the conventional 10-unit test system. Case 2. Unit commitment considering demand response programs. In this case, the total incentive and cost of generation have inverse trends, meaning that when one increases, the other decreases. The total cost of operation of the program generation units can be reduced after considering the DRPs, therefore, obtaining the optimal incentive value for DRPs is a complicated process. MIMP-UC-based solutions to the UC problem with DRPs are provided in Table 4. As shown, the total cost of operation of scheduled generation units can be reduced after considering DRPs. The MIMP-based optimum values of incentives have been obtained for the DRPs and are presented in Table 5. The output powers of generation units are presented in Table 6 after implementing DRPs. The shaded boxes highlight the difference in the power output of the generator units compared to the base case. As you can see, expensive generating units are not called at peak intervals due to reduced customer demand following the implementation of DRPs. For example, Unit 10, which is the most expensive unit in the 10-unit test system, is not activated at peak time. Applying the DR model to the initial load curve of a 10-unit system, the new load curve with DRP is represented in the figure, with a dotted stripe. Case 3. Unit commitment considering gridable vehicles. As mentioned before, it is assumed that GV are charged with renewable resources. In this case, the GVs are charged via the power grid. Their charging energy consumption must be considered in the charging curve and thus in the simulations. The implementation of GVs has reduced generation costs by shutting down expensive generating units at peak intervals. The MIMP-based solutions for the UC problem with GVs are provided in Table 7. The output powers of generation units are presented in this table after implementing GVs. As before, the shaded boxes highlight the difference in the output power of the generator units compared to the base case. The results of the proposed MIMP-based approach are compared with those reported in the literature. The table shows the comparison of the results of the MIMP-UC with the particle swarm optimization algorithm, PSO, using the same hypotheses considered in this study. It's no surprise that the exact method works better than metaheuristics, but it's surprising that the difference is so small. Case Study 4, Unit Commitment Considering DRPs and GVs. In this case both DRPs and GVs are considered in the UC problem. Table 10 provides the MIMP-based solution of the UC problem in the smart grid environment. The output powers of generation units are presented in Table 11 after implementation of DRPs and GVs. The shaded boxes show the difference in the output power of generating units comparing to the base case. The figure shows the difference in the market clearing price, MCP, between all the cases in the study horizon. MCP in the peak period is reduced after the implementation of DRPs and GVs. The reduction demonstrates the ability of DRP and GV to attenuate peaks. The results show that the smart grid has a significant influence on the UC problem, and if this influence is not considered, some difficulties in the optimal functioning of the system could arise. The results shows a significant reduction in the UC problem after including DRP, compared to the other cases. UC, 0%, UC plus DRP, 4.85%. UC plus GV, 2.27%, and UC plus DRP plus GV, 5.71%. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.